model it and then marginalize. Otherwise, I'm going to be marginalizing over like the whole range of the prior, not the specific like posterior for the data that it did have. And so that's a pain because I could have a lot of nuisance parameters. And it's also limited to like low dimensional posteriors, like tens, hundreds, something like that. So it's, yeah, so it's kind of like, it's really good if you have a good compressed statistics and you don't have a lot of nuisance parameters that you need to marginalize over in an amortized way. If you're not amortized, like if you have one universe you want to analyze, then it's a different game. But if you want to be amortized because you have a lot of different data you want to analyze, that could be a game killer. So NREs are this method of marginalizing over huge numbers of nuisance parameters implicitly. So if you're modeling, like you want to do hierarchical Bayesian inference, for example, so you care about one number, and you want to marginalize over a huge number of parameters like images or something like that, then this is really great. I'm not going to go into the details, but like what you want to do is you want to, like you're training a classifier basically that has to distinguish between two different distributions. So it has to distinguish between the joint of your parameters and your data. So theta is the parameters, x is the data, and the marginals of the two, the product of the marginals. So basically, you feed it like simulations with the parameter that generated the simulations and some simulation with some random prior sample that has nothing to do with the simulation. And the best thing that the classifier can do is basically learn the ratio between the two. Because if you just happen to give it like the parameters that give rise to the simulation, the network's going to be, well, it could be either, right? I don't know. So it's going to give you something that's not like 100% certain. So it's going to have uncertainty in its output. And that's exactly this ratio between those two distributions that it's going to output. So you can prove that this is the optimal classifier that's going to be predicting this ratio. And because you know your prior, then you can get your posterior out. So this is great. Sounds like magic. But there's a lot of caveats. So like the pro is basically that it can marginalize implicitly over a huge number of nuisance parameters because you choose what's the theta you want to predict. And everything else is just going to marginalize over it. But the problem is that because we've marginalized over all of these things, we have lost our ability to look at those nuisance parameters. So let's say that I'm going hierarchical inference and like I have like, let's say I'm a strong lenser, if you have not realized that already, because I have a lot of strong lensing example, but like I want to measure the temperature of dark matter from like images of strong lenses. So basically the step in my analysis pipeline would be I get an image, I infer the kappa map to find the subhalos, and then I use the subhalos that I find to find the temperature of dark matter. And so those like nuisance, so those kappa maps would be marginalized over implicitly here, and I would get directly the temperature of dark matter. But then if I want to know if I get a temperature and I rule out cold dark matter, I want to know where that signal came from. But I can't anymore because I've marginalized implicitly over it. So like people ask me, where's the signal coming from? Is it like a lot of big subhalos? Is it a huge population of small subhalos? And I don't know. It's been marginalized over. So I have no idea to like, and I have no hope of investigating my model. So that's kind of like really a bummer because if we want to trust this, we want to make sure that we can like learn things out of it. Like we need to be able to open the black box to understand where's the information coming from in our inference, and that completely does not allow that. And so and then another thing is that it's super brittle when you're looking at out of distribution data. So if there's a slight distributional shift between your simulation and reality, this is going to break in an extremely unpredictable way, like in a complete, because it's a super nonlinear model, and so this is going to break really bad. So that's not great. So that's basically the reason why we want to do better. So we have to do this. And so, all right. So this brings me to diffusion models. So do you guys have questions about the first part before I move on? Nope, everything's crystal clear. Great. OK, so basically, the diffusion model, it's a way of representing like very high dimensional and complex distributions and sampling from them. So this is like a problem that we have a lot. And so those like distributions can be like very complex and very high dimensional. So it could be that with analytical models, we cannot like represent them. So the question is, could we learn those really high dimensional, very complex, very multimodal distributions from data itself? So what does it mean? So basically, if I have like if I look at images of galaxies and I want to learn what's the distribution of galaxy and sample images of galaxies, every pixel is like an independent parameter. And so that's like if I have 100 by 100 pixel images, it's like 100,000 dimensional space. And images of galaxies, they live on a complex manifold inside that space. So here I'm representing it in 2D because I don't think in my brain in 10,000 dimensions because I cannot imagine that, but like 2D I can do. So that's like my density in 2D if there were 2 pixels. So it's going to be super multimodal. There's going to be lots of bumps and things. And so that's going to be a very complex like distribution. So if I wanted to fit something parametric to that, like a Gaussian, it would not do a very good job. So then the question is, like, can we learn this distribution from samples? Okay. That's where a diffusion model comes in. So yeah, so generative model in general, like is a field in machine learning. There's a slew of those things. And that's exactly what they do. Their goal is to learn a distribution and allow you to sample from it. So there's a lot of examples. There's like VAEs, normalizing flows, GANs. And so those are kind of like the old school traditional ones. And they kind of typically fall into 2 categories, the implicit models and the explicit likelihood model. So the implicit model, they don't tell you, they don't model like the likelihood of that data in that high dimensional space explicitly. They do it implicitly and they just sample for you. So like GANs are a way to do that. Then you never have to tell it like the likelihood of the data, but you have to train it like adversarially. So that's kind of really hard to train, and it's really prone to mode collapse and things, and it's bad. The other thing, like the explicit likelihood models, these are things like flows, where they model explicitly like the whole the density of the probability distribution of your data. And then it tries to preserve that density by mapping it from a distribution that you can evaluate, like a Gaussian, to the distribution that you didn't know by doing invertible transformations. So it takes every like little probability volume, it transforms it in a way that you can calculate the Jacobian of the transformation, and it maps it, and it splits it into like whatever distribution that you have. And then you can go back and forth between the two once you've done that. But that's really expensive because you have like those distributions that you need to learn, like those transformations that you need to learn like the Jacobian for. And so you cannot, it doesn't work in really high dimensions, basically. So recently, there's been a new generation of generative models that has gained a lot of popularity. Diffusion models are one example of that, but there's also like flow matching, there's like stochastic interpolance. There's like a bunch of family of these things, but these all fall within this new generation of generative models that work really well in high dimensions. Right. So I was going to say something, but then I forgot. So that's what we're going to talk about, diffusion models. So that's my game plan for the last 20 minutes. And this is a lecture that usually takes me 3 hours to get through. So we're not going to go very far. But I still wanted to give you all the slides so that you can have like access to it. So who among you knows what like an MCMC is, or has used an MCMC? Like almost everybody. Who knows what HNC is? A lot of people as well. So there's like, these are all like methods to sample distributions. Who has heard of Langevin sampling? 1, 2 people. Okay, so Langevin sampling is just like all of those other sampling methods. It's a way to sample a distribution. Okay, the same way that like Markov-Chain Monte Carlos are a way to sample, or Hamiltonian Monte Carlo are a way to sample, or like nested sampling is a way to sample. But Langevin, so just like all of these methods, its reason why it works is rooted in physics. And so this lecture sort of goes around like talking about what's the root of this way of sampling in physics. So that's what the first part of this lecture is. So are you guys interested in knowing about that? Yeah? Okay. So it's basically Brownian motion. So a particle in a gas obeys like F equals ma, basically. This is just F equals ma. And so for like the particle in a gas, like this is not a Hamiltonian system because there's drag, so the energy is not conserved. And so there's some like drag coefficient, there's friction coefficient like gamma, and then we know what it's given based on like the viscosity of the gas, right? So this is just like undergrad physics. And so the idea here is that the force in the gas is kind of, it's not known. So we don't know what the force is because we can write it as like a deterministic part that's like the gradient of some potential that we know. For example, the gravitational potential, or like if it's a particle attached to a spring, there's some like potential I can write for that. So any like conservative force, I can write a potential for. So that's the part that we know. But there's also the force that comes from the kick of all the other particles of gas. that are hitting that big molecule in the gas. And so that's going to be a source of like stochastic force that's on the particle, and I don't know what that force is. And that's basically what we refer to as noise. So that's the force that's due to the collisions of all the other particles. So what we end up with is like this equation here, and that is what is called a Langevin equation. So our goal here is that we want to solve this equation without knowing what the little f, like the noise is, basically. So we need to solve it without knowing what the force is. So like obviously, like what that means is that like if I knew what the collision were, like the series of collision that happened to my big molecule by like all the other particles of gas, I could solve for it exactly, but I would be something completely useless because it wouldn't tell me anything for what's going to happen like in the future because I don't know what the next series of collisions are going to be. And I also really don't want to have to solve for like all the series of collisions because I am not interested in solving Schrodinger's equation in like 10 to the 23 like dimensions. So I'm not going to do that. So what do we do? Okay, so what are we going to do? So basically what we want to do is figure out some crude properties of this stochastic force of this noise, like its average, for example. And then with that, we're going to try to learn some, or to calculate some crude properties of the motion of particles, like its average. So that's kind of our goal when we're solving stochastic differential equations. So we're going to start by doing some simplification. So first, we're going to assume that there's no external forces. So my potential is 0. So I can get rid of that. And then we're also going to assume that we have a very viscous medium so that the gamma is large. So I'm going to neglect the mass term. So it's like setting mass is equal to 0. So I get rid of this term as well. So what I'm left with is like the simplest possible equation for Brownian motion, which is this. And so if I knew like the specific series of collisions, like the force, I could calculate what the displacement of the molecule is like very easily. I just have to integrate it like this. But then I don't know what f is. That's like our whole problem. But so what statistical properties do I know about the force term? Well, I know that it's being kicked by a bunch of like molecules of gas, right? So on average, those kicks are going to be 0 because there's no direction that my molecule should be going on average. So I know that the expectation value for this little force that comes from all the kicks of the atoms of gas in the gas is going to be 0. So what that means is that on average, the position of my position is going to stay where it started. Wherever I put it initially, it's not going to move. So that's kind of deeply unsurprising. Okay, so on average, the noise vanishes. So on average, the particle will stay at the same place. Okay, so what about the 2-point correlation function? Can we say something about the 2-point correlation function of the noise? So the 2-point correlation function of the motion of the particle, then I need to know what's the 2-point correlation function for the noise term. So if we're in like 3D, I can write this like this here, because it's 3 dimensions of space, because that's the dot product that I have here. And so basically, now we have to do some assumptions. So what we're going to do is we're going to assume that the collisions are independent from each other, which is kind of reasonable. Like my molecules getting kicked by a bunch of like molecules in the gas. And we're also going to assume that the time scales that we care about are much longer compared to the time scale of the collisions. So because we care about macroscopic times, whereas like the collisions, they happen on microscopic timescales. And so we're going to assume that basically over the timescales that we care about, the collisions are instantaneous. And so because of that, we can basically write the 2-point correlation function of the kicks as a delta function in time with some coefficient that gives me the size of the kick. And because I know what's going on, I'm going to call the size of the kick d. Just something, because I know what's going to happen. I'm just giving it a name. It's d. It's the amplitude of the kick. So like the kicks are instantaneous, and they're uncorrelated with each other. OK, so now what I'm going to do is I'm going to plug that back in my 2-point correlation function for the motion of my particle. So I do that. So that's the first step, to calculate the dot product. And then I replace it by the correlation function that I just calculated. So the Kronecker deltas are going to contract. I'm in 3D, so that's going to give me a factor of 6. So I'm going to be left with this. And then I'm left with just an integral over time, which is easy. It's going to give me t. So what that means, what we've learned now, is that the root mean square of the displacement from the starting point is going to be scaling as the square root of t. So that's what I've learned. So if I put like a particle at some point, the root mean square of its displacement with time is going to grow as t. So and D is called the diffusion coefficient. That's why I called it D. But okay. So all right. So that means that average position is 0. Expected like the variance of the displacement goes as T. So what that means, I can simulate this on a grid, and then for a bunch of like every line here is a particle that I'm simulating. And so we see that like after 100 time steps, it's going to have grown by about 10. I don't know how many. I should have just made a movie. That was so idiotic. Okay, all right. Anyway, you see the point. I should have made a movie. I was too lazy. All right. So, okay, so I've solved this numerically now. So I'm going to show you how to do that. Because I had like a continuous equation. We need to discretize this, and like the North term is not super necessarily obvious. So the way that we do it is that we rewrite the stochastic differential equation like this here. Okay, so I've just split like that, and this dW is what we call a Wiener process. So what a Wiener process is that it's something that's almost surely continuous, and it also has independent increments. So what that means is that for every time larger than 0, the difference between the two values of the Wiener process are going to be independent of the past value of it, and it also has Gaussian increments like this. So every time I look at like the value of the Wiener process at some time versus some other time, it's going to be Gaussian distributed with a variance that scales like the time difference between the times that I evaluated, just like my Brownian motion. So this gives us a really easy way to solve the Langevin equation like numerically. And what I'm about to write down is basically just a stochastic generalization of like the Euler's method for integrating differential equations. So it's exactly like Euler's method, right? Like I start at some time, at some position at time 0, and then the time at t+1 is going to be, but at n+1 is going to be like whatever it was, plus the increment in the position that I had. That's going to be given by the delta of the Wiener process here. And this is going to be Gaussian distributed like that. So see how this is like the variance here. That's proportional to like the difference in the times that I'm looking at. So it means that sigma is going to grow like square root of t, because this is sigma squared. Okay? Make sense? So now I can integrate this like numerically. Yeah, that's the time step that I have. So this is how we do it. It's pretty straightforward. And now we can integrate it. All right. So basically what that means is that I can take my stochastic differential equation and I can simulate the path for one particle as it's getting kicked around. And it has the properties that I want. Like on average, it's not going to move. And it's like variance of its displacement is going to grow like t. So now we can look at the same problem in a different way. So for like one specific particle, like I cannot really say exactly where it's going to go. But clearly, I can talk about like what are the probabilities of finding a particle somewhere. So I can look at what's the probability of finding the particle at a specific position given that it was found somewhere at time t0. Okay? So like I've talked about it in terms of like the correlation function along one path, but this is like a different way of looking at it. So now what I want to know is what's the probability of finding the particle at some place, regardless of like how it got there, in a way that it obeys the same correlations as what the Langevin equation told me. So I'm not talking about like looking at the probability distribution over path. It's just the probability over positions of particle, because probabilities of path to go from one place to the other, that's a very different problem and very hard problem. So I'm just talking about what's the probability of finding the particle at x regardless of like how it got there, basically. Okay, so for the Langevin equation that I wrote down, I'm just going to tell you the answer for that. For simple Brownian motion, this is what this distribution is. So the probability of finding the particle at some position x at some later time, given that it started at the position 0 at some like at time 0, is given by a Gaussian distribution here. That kind of makes sense. Its variance is going to be going like t, so it means that the RMS of the distribution goes like square root of t. So it obeys the same correlations as like for an individual path as what we had before. So I can, and this probability distribution function obeys the diffusion equation, which is this equation here. So now this is why this is called diffusion, because it obeys the diffusion equation. So basically, the way that the distribution is going to change over time is going to be given by its like Laplacian like this, because the probability of the particle is not neither created nor destroyed. It just moves around in space. So, and this is the simplest example of a Fokker-Planck equation. So this diffusion equation is a Fokker-Planck equation that corresponds to simple Brownian motion. And you can tell it's important because it has a fancy name. So it's very important, okay? So I can simulate that on top of like trajectories. So initially I start all my particles at 0 with like, I should have made movies. I'm such a lazy person. But yeah, and I can overlay the probability distribution as it's changing with time. So like at some later time, my walkers, like my individual like solutions to the Langevin equations have gone to this place, and the probability distribution is the thing I'm showing with the colors. So it's kind of diffusing with time, and it's growing with time, and this is what I'm showing here. Do I have another one? Yes. Okay. So all right. So this is what this is for simple Brownian motion. So now there's like two different things that I have, right? I have the Langevin equation that gives me how to solve the path for like one specific particle as it gets kicked around. And I have the Fokker-Planck equation that tells me how the probability of a bunch of particles changes as a function of how they walk around. Make sense? And these are kind of two different ways of looking at the same process. One is looking at individual path, and the other one is looking at the distribution of particles as they're going around. Okay? So now let's make things more complicated. So let's say that I add a potential, so a deterministic force in my Langevin equation. So I have some general, whoa, what happened? Okay, sorry. So now I can still solve this like numerically by looking. They don't want me to talk anymore. Yeah, I think this is what we're going to have to do. Gonna go. All right, maybe. Okay, let's hope for the best. All right, so I can solve this numerically. So this is, again, just Euler's method, right? So my Wiener process is here, and this is just Euler's method. So this is how I would, like, if I didn't have noise, this would just be, like, I could solve this with Euler integration. So numerically, it looks like this. And then again, you see that this is proportional to, like, square root of t, and this is proportional to, like, the delta t that I have, right? So this is what it is. And so I can solve numerically my Langevin equation to get the path of an individual like particle as it gets like, so it gets like moved by the potential and also kicked around. So there's those two things competing to make one particle move. But I can also find if I drop a bunch of particles, how they're all going to move together. So that's the Fokker-Planck equation. So deriving the form of the Fokker-Planck equation involves some math magic that I'm not going to talk about, but this is what it has. So that's the form of the Fokker-Planck equation here. So basically the distribution of all my different particles, like if I drop them at some place, is going to be, how that distribution is going to change over time is going to be given by these things. So there's a part that's like the drift term that gets driven by the gradient of the potential that wants to deterministically make my particles move. And there's also the diffusion term that makes my particle just want to walk around, right? So now we have turned like a stochastic ODE into a deterministic PDE. This is a PDE because it has time and space derivatives. So this is very interesting because we have this like two different ways of looking at the same thing. One is stochastic that we cannot solve like deterministically, and the other one is deterministic, and we know exactly how those particles, like if I have a bunch of particles, I know exactly how as a collection they're going to move around. Okay, so why am I talking all about this? Because of sampling. Okay, because I can turn this into a sampling algorithm, like a legit sampling algorithm. So basically I have like, so how can I do that? So if I find a potential that exactly balances my source of noise that wants to make my like particles diffuse, I can end up with a steady state distribution for my distribution. Like basically when I was here, like if I find the value of the potential here that balances this guy here, I can basically find a way of make this time invariant. And if I initialize my walker according to that distribution, then they're not going to, like as a collection, they're not going to move with time. So what that means, I can solve the stochastic differential equation. All my individual walkers are going to be moving around, but at the distributions, they're just going to be distributed like P, like that distribution. And so I can use the stochastic differential equation to sample the P, is what it means. It's like if I have kids like on a trampoline, like every individual kid, and there's a lot of them, like every individual kid is like moving with time, but then as a distribution, they're like a steady state, and they're constantly, like they're distributed in a way that's constant, but then every individual kid is just moving around. And if I take a snapshot, then every kid is like a sample of the whole distribution. So I can use those walkers basically to sample a potential, if I can figure out what's that potential, basically. So that's kind of like the idea. So we can turn, okay, this is the most beautiful part, but I'm out of time. But, okay, so you can actually like figure out what's the equation for the potential you need to put there. And because of math, it works. And so, so basically, like if you write this potential, if it's like some energy function, that's like an exponential function like that, you can sample that distribution. That's the thing you need to put in your stochastic equation, in your Langevin equation. But the thing that goes in the Langevin equation, remember, it's like the grad of the potential, but then, and then it's going to turn, if I put this here, like the grad of V, and that's the V, then solving the Langevin equation is going to give me samples of pi, basically. That's the relationship between what's the potential that I put and what's the distribution that I end up sampling. So if I use this trick, just the exponential of the log of the distribution, then I can turn this in a way of sampling any distribution that I want. Because there's a relationship between the V that I put in the Langevin equation and the distribution that I'm going to end up sampling. So if I put this V in the Langevin equation, then I end up sampling this pi once I reach a steady state. Okay? And then the magic is that what goes into the Langevin equation is the gradient of that potential. And so the thing that's really hard is that when we have distributions, we need this normalization constant here that's like really messy to evaluate. But when I take the gradient, that normalization constant just goes away. So I don't need to care about it. So in my Langevin equation, I just need the gradient of the potential. So I don't need to care about the normalization. And I can produce samples of the pi distribution that I can care about. Does that make sense? Okay, so there's no machine learning here. This is like a legit sampling algorithm. You can just sample with that, okay? So this is, it's called, in machine learning, this is called the score, hence score-based modeling, okay? So, all right, so this is a way to sample. So I can sample like any distribution that I want. So I can turn this into like blah, 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 whatever. So this is an example. So if I have this distribution here, that's kind of messy. It looks like this. I can sample it like this by solving the stochastic differential equation and letting it reach like a steady state. So these are samples from this that I've sampled with Langevin, unadjusted Langevin sampling. All right, so score matching. So where's the machine learning in all of this? So basically, now we have a way to sample any distribution we want that does not require us to know the normalization constant, only if we know the score of the distribution, right? I just need to know the gradient of its log, and then I can sample it. So can I do that? Can I learn that from data? So like, again, I have like some training data, and I want to learn this quantity here. So like if I wanted to learn this distribution, I could try to learn the density. Like let's say those are galaxies. I could try to learn the density of the distribution directly. By like minimizing the KL like between the likelihood of the data and my like estimator that I have. But that's going to be really hard for a neural network to learn, because learning the density, the thing that's hard with it is that it needs to know about information from everywhere, because it's like the density depends on that normalization constant. So the neural networks need to know about where all of the information, like if there's another mode somewhere else, it needs to know about it. And it needs to know how much mass there is in that mode to be able to know what's the amplitude that the density should have. So learning the density for a neural network is really, really, really hard. But learning the score, which is just a vector field, is really easy. Because it's a vector field, it's a gradient, it only requires local information. And that's something that neural networks have a really easy time learning, because they have all those convolutions that learns about local information about those things. And so it has exactly the right inductive bias to learn this thing really easily. So score-based modeling is basically teach a neural network to learn this from these training data. And then once you have learned that, you can just plug that in your sampling method, and then you're done. OK? So what do we have? We have some like IID samples of our like data generating process. What we want is to estimate the score with some neural network. And so it's going to be a model that's going to be a vector value neural network that's going to represent the scores. It's a function from Rn to Rn that we want to learn. So that's exactly what the unit thing that we talked about yesterday is good at, because we give it an image, it's going to output an image. So it's exactly a vector in that like 10,000 dimension space. And so what are we missing? We need a loss function that's going to tell us how bad we're doing, right? And that loss function needs to be a scalar that we can take gradient of to optimize the weights of our neural network. So like basically, we need a way of saying if this is the true score and my neural network is doing that at a bunch of different points, like how bad is this? So the simplest thing we could say that we're going to do is we put them on top of each other like that, and we take the average of the norm of the difference between the sets of vectors. So that is like the Fisher divergence. It's like this. But then there's a problem is that we don't know what this guy is. Like we don't know what the real score from the data point is. So we can do more math magic. So there's in the notebook I'm going to give you, there's a way to like solve this problem. There's a number of ways to solve this problem. I'm going to tell you about a different way to solve the problem and the one that's like implemented. So we can use it using, you can solve that using score matching, which is pretty old. So basically, we integrate by part, and we do a bunch of tricks, and then we can rewrite this like this in a way that does not depend on the distribution that we do not know, only the thing that we're trying to learn. So this is the trace of the Jacobian of the score model. It's kind of hard to evaluate in high dimensions, but there's a way to do it efficiently. So actually, now we're really golden. We have a way to learn the score. We have a loss we can optimize. We can just learn the score and be done. So then the question is, why are we not done? So I can do that on like CFAR, which is like the same data set that I showed you yesterday. And I can use this method to learn the score and then sample more CFAR 10 data. And then I get this. And this is garbage. Like very obviously garbage. So why is this garbage? Why is this not working? I had all this math and this physics. Like I just talked for half an hour about all of this, and it's just not working. The reason why this is not working is that like my neural network can only learn the score at the place where I have training data. So the places where I have training data is the places of high density. It's in this mode and in this mode. So what's going to end up happening is that like I'm going to learn really good scores here and here, but everywhere else it's going to be garbage. Like it's going to have as if like I didn't have any training data. As if I had no support there. So, but when I'm sampling, I'm going to sample from like anywhere because I don't know where the high density region is. So I'm just going to start by like a place like random noise, and the score my model is going to have learned there is just a random direction. So like I'm never going to land in the high density region if I don't start in an already high density region. But let's say I'm trying to sample like the faces of people. Like what's the probability that just by randomly sampling an image, I sample the face of a person? Like it's like zero. It's like popping a Boltzmann brain out of vacuum fluctuation. It's not going to happen, right? So I mean, this is just not going to work. So what can we do? So the solution, yeah. Right, we don't know how to land in those high vector space. So the solution is annealing. So what can we do? We can just say this is the distribution. This is where I have good like samples with my scores. I can just anneal my distribution and make my distribution wider and wider and wider and wider all the way until it covers all my parameter space. And then I can sample anywhere and I can land at the right place. Right? Doesn't matter where I start. I have good scores everywhere. So I can train a bunch of different score models for all those different like temperatures of annealing. And then I start sampling here. And then once I manage to converge somewhere, I just go down temperature, keep on sampling, and then go down and keep on sampling until I land on my manifold, and I keep on going like that all the way up to my zero temperature manifold. That's the one I want to sample. And then this is great. And then this is going to work. So now the question that you might have is, all right, so how many different temperatures of this do I need to do a really good job? And it sounds like I should have infinitely many. So yeah, so we learn a conditional model, blah, 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 and that's a unit that's conditioned on the temperature. OK, perfect. So how many noise levels should I include? It sounds like the best thing to do would be to have infinitely many to ensure very good transitions when I change the noise level. But when we've done before, like we know exactly how to represent the process of noising up samples with like almost certainly continuous kicks, right? This is a Langevin equation. So I can just noise up my data by adding noise to it up to the point where it covers like the whole, it becomes just like a Gaussian distribution, basically. And then I know how to represent this because it's the process of noising by adding noise to my data. That's just a Langevin equation. So this equation that we talked about a lot. So I have my target distribution, and then I add noise to it by adding noise to it with the Langevin equation up to the point where the distribution of my images, they're just randomly Gaussian, like this, they're Gaussianly distributed, basically. So it's going to look like that. Let's see, this is just one sample, but I do it to all my samples. So like as a population, they all become Gaussian distributed in this like 10,000 dimensional space. So this is one image. I just keep on adding noise to it until I have destroyed all information, and it's just random Gaussian noise. So this is one sample of a Gaussian distribution in like many million dimensions, okay? Not millions, like 200,000 dimensions. Okay, so now we know, so now I can train like my score model. So now I use this to train a score model. But I know that like at every noise level, the distribution of images is going to be distributed like the solution to the Fokker-Planck equation, right? Like the marginals for all of those images at different noise level, they're going to diffuse around like the Fokker-Planck equation, because that's what we talked about. Like one random marker walks around like one realization of the Brownian motion, but like a bunch of walkers together, they diffuse around according to the diffusion equation, like the Fokker-Planck equation. So I know that, you know, at every noise level, the distribution of all my different galaxies are going to obey this equation here. But then it turns out that actually there's a reverse time stochastic differential equation that I can write down that's going to satisfy exactly the same Fokker-Planck equation. So this one is just a deterministic one, right? But then I can write down a different equation, that stochastic equation, that goes backwards in time, that obeys the same Fokker-Planck equation. And that's a reverse time stochastic differential equation that starts from my simple Gaussian distribution and denoises according to a reverse time stochastic differential equation that ends up at my target distribution. And I know it's the target distribution because it obeys the same Fokker-Planck equation. And so that allows me to start from noise and slowly denoise my samples by solving this stochastic Langevin equation, this reverse time stochastic differential equation, and then landing on a different sample from my target distribution. Okay? So I'm not like removing noise, like I'm going to land at the same sample. No, I'm just going to land at a different sample from the same distribution. And what I need to know to write this reverse time stochastic differential equation is the score of the distribution that I care about. So using the noising process, I learned the score. The score is represented by a neural network. And then I take this score that I learned, this machine learning model, and I just plug it in this equation, and I just solve this equation to get samples. Okay? But the sampling process is just a legit like sampling process. It's just that there's a piece of it that comes from having learned a neural network. Okay. So I'm like really out. Oh no, not too bad. Just 10 minutes over. Okay. So this is diffusion models. So you can learn any distribution you want like this now from samples. And I have like at the end of my thing, I have like two very cool notebooks that my grad student Alex Adam wrote. And they're very cool, and they give you a lot of intuition for how to write one of these things to sample distributions, like analytical distributions. And he also wrote a really cool package so that you don't have to do all the coding of the neural network. And he has a training loop and everything and a sampling thing, so you can use his package to sample. It's very well written. So all those links are at the end of the thing. If you guys want, I can give you examples of how to apply this, or I can just stop here. It's up to you guys. Raise hand if you want me to stop. Nobody wants me to stop. Okay, so I can give you maybe just one or two examples on how to use that. Sounds good? Okay. So I care about this to solve inverse problems. Like I've already talked about inverse problems yesterday, so the variables are defined differently than what I said yesterday, but this is basically my vector of data. This is the noisy data that I have. X are the parameters that I care about. F is some function that represents my forward models. That's like the physics that I know about. And Z is some vector of like additive noise. So I know about Bayes' theorem. So what I want to do is I want to sample this posterior for the parameters that I care, given the data that I observed. So that's going to be given, so that's the posterior, that's what I care about. It's going to be given by the likelihood times the prior divided by like the evidence, which is a normalization constant. Okay, so in the case of a linear inverse problem, this forward model, this F function is just a matrix. So it's just a matrix multiplication. So an example of this is Alex, is like strong lensing source reconstruction. So in strong lensing, like the mass distribution in the lensing galaxy is really, really nonlinear. But then once I know what this is, I can package all of that into a nice lensing matrix A. And then the deformation of the background source into the lens image is just a linear operation. So basically, if I have some noisy observation of some lens and I want to reconstruct the background source, but like I know what the lens is, I can phrase that as like a linear inverse problem, like this, with some like noise here. Okay, so what I need to know to be able to sample that, I need to know the likelihood. So to know the likelihood, I need to know the physical model, so that's the matrix A. And I also need to know what's the noise statistics of my noise, my additive noise. So that's the noise model. And that allows me to write down the likelihood because the residuals are distributed like noise, right? So if I know the noise model, write the residual, plug it in there, should be distributed like my noise. And then I also need to know what my prior is. So that's a place where it really pays. Like for galaxies, it's really hard to write an analytic function for what galaxies look like in all its glorious details. So I can basically train a score model to represent my prior over what galaxies should look like. Right? And then once I train that prior model, I can just use low redshift images of galaxies, and then I can sample new images of galaxies. So these are galaxies. Some are real, and some are not. And I don't know which is which. So don't ask me. But you can go to this website and generate fake galaxies. It's really fun. And then so all the ones you generate on that website, they're not real. But they look really realistic. Like they have a lot of like features and like complex morphologies and everything. It's like they look beautiful. Okay, so that's my prior, basically. So my prior is like the prior over the possible distribution of galaxies. But what I want is not the prior. I want posterior samples, right? So if I want to have posterior samples, I need the score of the posterior, because the only thing I need to sample distribution is a score. So I need the score of the posterior, but I know Bayes' theorem. So I can write this as the score of the likelihood plus the score of the prior minus the score of the evidence. So now the evidence, I know it's a normalization constant. So that's just 0 because it doesn't depend on X. So that's great, no evidence. I also know the score of the prior, because that's the score model I just trained. And so the only thing I'm missing is the score of the likelihood. So the score of likelihood is a little bit tricky, but I know my forward model, like the process of lensing. So I know the A matrix. And if I know that my noise is Gaussian distributed, I can actually approximate this with like a very good, pretty good approximation. There's a lot of work that's been developed like in the recent years. So there's a bunch of different approximations we can use to approximate the score of the likelihood. So that can be done like analytically. So once I have that, I can just sample. So let's say that I have, this figure is a bit busy. So let's say I have this. So this is the ground truth background galaxy that I have. And this is the model that I have. So what I can do is I can generate a bunch of mocks with different levels of noise. So these are my mocks here. So this is like the mock data as a function of how much noise I have in it. So if my signal to noise is really, really large, there's a lot of information in my likelihood. Up there are the posterior samples that correspond to it. So there's a lot of information in my likelihood. So when I do posterior samples, they're going to have very little variation between the different samples because the data is really constraining, basically. So the uncertainties are really small. So I basically almost don't need my prior because the likelihood is so constraining. So that's what it's showing here. But then as I increase the amount of noise in the data, there's more and more information stored in the likelihood. So that information needs to be filled in by the prior. So that's what's happening. So there's more variability across the posterior samples. And then the thing that's really cool is that in strong lensing, like the thing that lands exactly behind the lens is magnified by a lot. So here it's like the center of the background galaxy. there's a lot of information in the likelihood frame because it's like magnified and stretched. So in the posterior samples, the center is always reconstructed with a lot more consistency across the sample because it has like higher certainties, has smaller uncertainties. But then the outskirts of the background galaxy, they get drowned in the noise because the information's been like, the information's been destroyed here in the likelihood. And so there's a lot more uncertainty, so that information comes from the prior. So it gets basically interpolated between like the very certain background center and like prior samples from galaxies that are much less certain, basically. And then in the limit where there's no signal in the data, I see just noise. I don't have any information about the background source, so I just get a random prior sample as my posterior because I didn't learn anything. So this is cool. It does exactly what we think it should be doing. So I can look at how bad is it when I'm out of distribution, because that's one of the famous things that I've been talking about. Like if you don't know your prior, is it going to be biased? Or is it going to give garbage? So we can look at what happens when we have a galaxy in the shape of a 7. So I wanted 42, but that was at the time when DALI wasn't very good, so we didn't manage to get 32, so we had to settle for 7. So 42, sorry. Anyway, so 7, so this is a galaxy prior that I have to analyze this data. So like 7 is really out of distributions because they typically don't really look like 7. So this is my true background source. This is my model. And again, it's the same thing. These are mock observations with different levels of noise. And these are my posterior samples using my galaxy prior. So in the case where there's really high signal to noise, there's so much information in likelihood that I don't really need the prior. So I can reconstruct the background 7 really well. But then as I increase the amount of noise, there's more and more information that's been destroyed in the likelihood. So the posterior samples are going to pull information from the prior to fill in like the outskirts with galaxy information, because that's what my prior is. But then you see like this middle of the 7 is reconstructed with more certainty because that's the place that's more magnified. There's more information about that in the likelihood. And then in the limit where it's just noise, and I just get random galaxy samples because I have a galaxy prior, right? So it does exactly what we think it should be doing. And it's very interpretable as well, because I have access to my posterior samples. So if I see signal, and I can quantify like with what certainty is, say, like a specific spiral arm reconstructed, because I can count like in how many posterior sample is it there on average. Like, but on average, it's like if I have a bunch of samples, it's there in like 68% of my posterior samples. So I have a 1 sigma detection of that thing, basically. Yeah. So that's using score-based priors. Are you guys up for more? You guys want to do more? Okay, so I said that like we needed to have a Gaussian likelihood, right, to approximate our likelihood. But then this is noise. There's no signal in there. This is like just noise from HST and noise from GWST. Do you guys think this is Gaussian? It's not Gaussian. There's a bunch of cosmic rays, and like even like the readout noise is like super. GWST is very famous, but it has those like stripy correlated noise. It's a hot mess. Like data in real data always has very messy noise properties. So assuming a Gaussian likelihood is rarely a good approximation. So what can we do, right? That's a shame. But okay, but then the thing is, like, we have this method that can learn the distribution of anything if I have examples. And it's not that hard to get noise. I just have to look at nothing and expose, right? So or I can just look at darks, and I can get noise samples. So I can take parts of my data where the signal that I care about is not there, and then use that as sample to learn the distribution of the noise. And then I can sample that noise. So these are fake noise samples from HST and GWST. Compared to, so these are real, these are fake, and they look really realistic. So I can use that to do like, to simulate the noise if I want to do simulation-based inference, like really realistic noise to have super realistic simulations. Or I can use that as my likelihood distribution, because I know that my likelihood is the noise distribution if I plug in like my residuals. So we can do that. So this is what I learned, and it's actually the likelihood. Because my noise my residuals should be distributed like the noise. So if I want to sample my parameters, this is what I need to sample. This is just the Langevin equation that I wrote down, right? But that gradient here with respect to my parameters, that's not what I learned. I learned the gradient with respect to my pixels in my data space. So what I'm going to do is I'm going to use the chain rule to get the gradient of my physical model here. And if you code in PyTorch and your physical model is like differentiable, you have that for free. This is just, you just get it. So now you can sample your parameters, and this is what you get. So this is some data that, it's not data, it's a mock. I have injected some strong lens signal in a real patch of HST noise. If I had assumed that that noise was Gaussian, I would have gotten the blue contours. Extremely biased, because it's the wrong noise model. But then with this data-driven likelihood, I get the correct like posterior sampling. And I can look at the coverage of these posteriors over multiple different examples, and we see that like we're calibrated, so it's great. Yeah, and this is super useful because like it could be used for gravitational waves when you have like glitches that you don't know how to like model analytically, and you can use glitches as part of your noise model. You can use it for a spectroscopy with JWST when you have like 1/f noise that's really hard to handle. You can use it to do like PSF deconvolution and denoising with your regular data if you want to do super resolution. And you can even use it to do like interferometry if you want to reconstruct, like if you don't want to use clean because you're Bayesian and you believe you should have uncertainty in your reconstructions. So there's a lot of applications. And I think I'm going to stop there because you heard me talk enough. So I'm just going to go like super quickly through how do we know that those posteriors are accurate, and just show you the notebooks where you can go play with that stuff and the package that you can use to model the score of distributions if you like. So that's it. The slides are already in the Slack channel, so